Learners, back with another video. Today we are going to discuss about the effect of substituents on acidity of phenols. In last video we have discussed acidic behavior of phenol, but how substituents will affect this acidic behavior. Today we will be taking this. But before starting this, we should know about some terms. First I am taking the hyperconjugation. Conjugation. These terms are necessary because these will be used further in your further concept. Hyperconjugation is also known as no bond resonance. Fine. In hyperconjugation, what is happening? See, the electron present in sigma bond will interact with adjacent empty non-bonded, or we can say anti-bonding pi orbital, or we can say pi bonding orbital. So this interaction results in the hyperconjugation system. Due to this, there will be stability in the system. It leads to stability of system, and it also increase delocalization, increase the electron delocalization. So to explain this hyperconjugation, we'll take one example. So I am taking an example, that is ethyl carbocation. How these are showing hyperconjugation? See, carbon attached with the 3 hydrogen and then CH2 positive. This we are numbering them. First hydrogen, this one is H1, this one is H2, and this one is H3. Here transfer of bond will be taking from this to this, and then we'll observe a structure. So here we are having H2, single bond carbon, double bond CH2, positive, no positive, because we are shifting the electron now, so positive will not be there, positive will. Here is a loss of electron, so positive H1 will be having the positive charge, and here H3. Then further transfer of electron will take place from here to here and here to here. So we'll be having H2. There is loss of electron, so positive charge carbon, double bond CH2 and single bond H3, and here develop H1. Okay, and further there will be transfer from H3 to this one and this to this. So what will be the structure? So here we will be having H2, single bond carbon, double bond CH2, here H1 is here, H3, loss of electron is from H3, so positive charge will be here. So overall structure, what will be having? Overall structure, what will be having? Will be having carbon, single bond CH2, H2, H1 and H3. So here the bond is denoted with the dash because it is breaking and forming, and here it will develop partial positive charge, here it will develop partial positive charge, partial positive charge, partial positive charge. So this will be your hyperconjugated structure. It leads to, helps in the stability of system. This helps in the stability of a system. So this concept we will use further in your effect of substituent. Second thing that is used, that is the inductive effect. Second we are taking that is the inductive effect. See, in inductive effect there is polarization of sigma bonds. Fine, and this is due to electronegativity difference. There are two types of inductive effect. First one is electron withdrawing inductive effect, and second one is electron donating inductive effect. What is the difference? See, in case of electron withdrawing inductive effect, it is known as minus I effect, and this one is known as plus I effect. Okay, see, electron withdrawing inductive effect shown by the electron withdrawing group. We are taking a carbon chain, carbon, 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 and here we are having a group which is more electronegative. This group is more electronegative. Okay, when this is more electronegative, group will have more tendency to attract electron towards itself, so it will develop partial negative charge. By loss of electron from this carbon, it will develop partial positive. The loss partial positive, partial positive. So with distance, inductive effect decreases. Fine. And in case of electron donating group, we are taking another chain which is having some electron donating group. So electron donating group, this is less electronegative, so it will be having partial positive charge, partial negative, partial negative, partial negative. It is electron donating group, it is giving the electron. When it is giving the electron, there is a loss of electron, there will be gain of electron. So with distance, it will be having more electron, then less further. These are the electron donating inductive effect. Okay, resonance effect. Resonance effect. This is also known as mesomeric effect. Okay, this type of in this type we are having two types. We are having minus R effect and plus R effect. Minus R effect is shown by that group which withdraw electrons. Fine. Suppose we are having a chain carbon, 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 and here we are having some X electronegative group, electron withdrawing group. Electron withdrawing will attract electron from this carbon and this carbon. So electron density will decrease on this chain. So due to this, electron density is decreased. Fine. Here we are having some examples of this: nitro, cyano, carboxylic, and sulfonic. Okay. Whereas in case of plus R effect, these are shown by that groups which donates electrons, and the molecular entity which is left, that will acquire here it will donate electron to this chain. So electron density is increased on the molecular entity left, is increased. Here we are having OH, some examples: thio alcohol, alkoxy, amino, secondary amine. Getting a point? See what is happening? This is electron withdrawing group. It will attract the electron from this. So after withdrawing the electron, the molecular entity which will be left, that will be have electron density decreased. And in this case, electron density is increased on this chain. The molecular entity which is left, the molecular electron density will be increased on this. So electron donating group, electron density will increase, electron withdrawing group, electron density will decrease. That is minus R effect, this one is plus R effect. Fine. So we will be taking the effect of substituents on acidity of phenol. As we know, phenoxide is the stable phenoxide ion. This phenoxide ion is stable, and that was due to the greater resonance. Resonance makes it more stable as compared to phenol. It was more stable than phenol. And second was, first was the greater resonance, second dispersal of charge. Due to these two reasons, this phenoxide ion was more stable. Okay, stability of ion. Now we are talking about the substituents. If phenol is attached with some substituents, what will be the effect? That means we have to discuss about it, acidic behavior. That means how acid is formed. What is acid? Release of H+. That means when any electron withdrawing group or electron donating group is attached to this phenol, it will be greater acid or it will be weaker acid. We have to know about this. So we have to see whether this H positive release is easy or difficult. If it is easy, that means it is greater acidic in nature. If it is its ease is difficult, that means it is weaker acid. So first we'll be taking the electron withdrawing group. How electron withdrawing group affects the acidic character of phenol. Here we are having some examples of that: nitro group, cyano and halide. These are the electron withdrawing group. Electron withdrawing group increases the acidic strength. It increases the acidic strength. Why they are increasing the acidic strength? Because it is stabilizing the ion. Because it is stabilizing this phenoxide ion. This phenoxide ion is stabilized by electron withdrawing group. So this stability makes it more acidic. Fine. Because dispersal of charge is perfect. Yeah, you can say is good. Dispersal of charge is intensified by attaching electron withdrawing group to the phenol. Okay, when electron withdrawing group, any nitro, cyano, halide group is attached with this phenol, that increases its acidic strength. This happens because this helps in stabilizing the ion, that is the phenoxide ion, due to the dispersal of charge. But this is all about the electron withdrawing group. Now, if position, we know the position: benzene, ortho, para and meta. Ortho, para and meta. How these positions are related and how we can say that ortho is more stable than para isomer is more stable than meta. So we'll discuss about this. Stability of nitro is due to minus R effect and minus I effect. I have already told you about these two effects. Thus electron withdrawing group is shown by minus R effect is shown by nitro, and minus I effect is also shown by the nitro group, electron withdrawing group. So these effects makes it stable. So this is more acidic. Acidic strength is increased due to these effects. Fine. So now we will be taking the isomers: orthonitrophenol, paranitrophenol and metanitrophenol. We'll discuss about the acidic behavior of these isomers, which is more acidic and which one is less acidic. Fine. So how they are more and or less acidic. First I am taking the orthonitrophenol. Orthonitrophenol, double bond O negative. Here nitrogen is having positive charge. Okay, so here transfer of bond is taking place. Actually this bond should be here. I am making it another way. Okay, transfer will show in this way. See how movement of electron is taking place. This will be moved here, and this electron, this will be moved here, and this will be moved here. Fine. So here we'll be having double bond O, movement of electron due to this electron was moved. So we are just taking the another resonating structure. So here we'll be having bond, here we'll be having bond, here that is the movement. So here we are having double bond, nitrogen, single bond oxygen negative charge, single bond oxygen negative charge, and nitrogen is having positive charge. Fine, this is your structure. And what is the byproduct? That is the H plus. H plus is released due to its acidic behavior. Fine. Okay, this is your orthonitrophenol. Orthonitrophenol. Okay, second we are having paranitrophenol. Para, double bond O, nitrophenol, positive. Here we are having oxygen, hydrogen. This one, how transfer is taking place? See, this bond is moved here, this bond is moved here, this one here, and this one here. Okay, so here we are having, see, nitrogen is having double bonds, N, single bond O, negative charge, negative. Here we are having positive, and here we are having double bond O. This bond is moved here, so this is formed, and here we are having H positive. So here again this release of H positive is there due to acidic. Fine, this is your paranitrophenol. Okay, next we are having metanitrophenol. See, metanitrophenol. Here this Nitro group, this electron withdrawing group shows minus I effect. Due to minus I effect, the release of H positive is very difficult. So this is your metanitrophenol. See, now we have to see whether orthonitrophenol is more acidic or para or meta. First, in orthonitrophenol, the structure formed, the orthonitrophenol is having ortho, I'm writing it here, orthonitrophenol, O, H, and double bond O, E double bond. Here we are having negative charge, positive. Here we are having intramolecular hydrogen bonding. In this orthonitrophenol, we are having intramolecular hydrogen bonding. Due to this, release of H positive is slightly difficult. But in case of paranitrophenol, minus R effect makes the release of H positive easy. Minus R effect makes the release of H positive very easy. Due to this plus R effect, paranitrophenol is more acidic and metanitrophenol is less acidic. So we are having a order: paranitrophenol is more acidic than orthonitrophenol, which is more acidic than metanitrophenol. Paranitrophenol is due to minus R effect. This is intramolecular hydrogen bonding, and this is due to minus I effect. This is all about your electron withdrawing group. Next we'll be taking the electron donating group. Thank you for watching the video. Don't forget to like and subscribe.